Thank you very much. I'm going to give a talk entitled Secure the Clones, and the topic is about how to define and enforce policies that will allow to do object copying in a secure manner. In the setting of the of complex collections of classes that might be more or less trusted, and we have objects with certain content that we might want to protect that run trusted parts, and there is a certain way in which you can enhance security by doing the proper amount of copying of objects. In fact, that's not just our observation, it's something that you will find in the guidelines provided, for instance, by Sun, but they also find them in the OWASP guidelines. So here it says that guideline 2.22, create copies of mutable output. So the point is that if you have a method that will return modify the internal state. So they suggest that copy mutable objects before returning them, unless of course you explicitly want to share state. And to create a copy of a trusted mutable object, what you do? Well, you should call a copy constructor. So Winnie reads this guideline and says, okay, here now I have my bookshelf, so I should clone this thing and then make a reference to it. In this case, he is happy because now he can store his things in a place where the coyote will no longer be able to put his hands on it. Again, cloning is simple in an IKEA world, but when we get into Java, the problem is that there's no default way of copying these objects. And actually, copy methods must be provided by the programmers. So you can do this in several ways. You can implement, say that this is explicitly clonable, so it should implement a clonable interface, and then you have to provide a method clone that will do the copying that you want to do and return a reference to an object. Or you might use what they call a copy constructor, particular constructor, which will take the thing you want to copy as an argument and then do the proper copying. Now, when we're talking about cloning and copying, in this world, as I said, there's no default copying, and that's because you can do, of course, copying in several ways. So you're probably all familiar with the notions of shallow and deep copying, but just to recap on that. So here we have a list where we have a spine of blue elements, and then in that there are references to the actual elements of the list. Now, if you want to copy this thing, you can do it in several ways. You can copy the list where you copy the deep, which means that you copy both the spine and also each element of the list. So now you really have something that's completely distinct, or just identical but distinct in memory. So that might, of course, achieve a certain separation between data, but it also has a certain cost, especially if the red things here are of a certain volume. In which case you might actually want just to keep a reference to this and share these things. So you get into, instead of copying the elements, you just copy the spine of this and make this shallow copy. And there you keep references to the actual original elements, which then become shared. If you want to do this, saying the same thing in ASCII, then so if you have a list here with just values and next element, then the constructor will just initialize these things. And then you might have these clone methods. Well, the basic clone will just return a new element allocated here, where it reuses the value that it receives, that you find in the element that you want to copy. If you want to do some deep cloning, then you would explicitly have to copy that element, and you might do it in this way, and then call the cloning method recursively on the list. So those are different ways of doing it, and there are even other complications to this. I mean, subclassing and overriding will complicate matters even further. So here's a short example from copy on output, where you have a private final field date. So the field is final, but the content is still mutable. And when you later on have a method that will return the date, then you'll return a copy to it. But there's nothing that actually guarantees you that just because it's called clone, that it will actually return a copy, or what kind of copy it will return. And it might even get into trouble because this you might call an overwritten version of date point clone. So there's little control over what actually happens when you do this cloning. What we are looking for is sort of a language for expressing copy policies that allow you to say what you want, how you want your objects to be copied. So this language should be expressive enough to copy a reasonable amount of policies. We'd like it to be simple, though, and also to work in a modular fashion that respects the structure of the language. In particular, it should be compatible with subclassing and the method overriding. And we'd also like to be able to make the link with the underlying programming language, so there should be semantic foundations for this policy language, should be part of your integrated with your programming language. Next thing what we want is that once you have this language, we want to make sure that you can actually enforce these policies once you have declared them. So you want a mechanism that's sound, which takes advantage of the semantic foundations that you've developed here and prove it sound. It should be precise enough to deal with reasonable clone methods, but we don't want a full strength shape analysis that can reason about any kind of memory structure or properties that you want. That's these policies that will inform the sharing aspect of it. And importantly, the policies can be checked in the presence of overriding, so you can do this in a modular fashion and impose constraints that cannot be circumvented by redefining clone methods. And we do this by accumulating these constraints on the deepness of the copies. So what we suggest is to take these classes and then add copy signatures on certain methods that we identify as copy methods. So it's not something you have to put everywhere, but it's a policy that says that this method will respect a copy policy, and then you can use that and annotate that to show that this is your policy. So the idea is that we flag these methods as give them a copy policy, which here we give them a name default, and then for each element in the structure we say how they should be copied. So basically shallow saying that, well, you can share references to this, you don't to be deep copying this value. And then you can say that other fields, they might be flagged as deep, and then you can use here, because you have a recursive structure, you can use the name of the policy to recursively say, apply the policy recursively to these fields. So that's the basic idea of the language. And here we have a default copy signature that we might actually be able to associate with the class itself. So that would be the default copy signature for that particular class. Values copied shallowly, and this copied deeply. And then you just say that this is the basic copy method for that particular class. But of course, the idea is that we want to be able to specify several methods with respect several different policy classes. So we will also have this so in addition to the default versions, you might want to specify explicit copy signatures to show that this method respects more involved copy policy. So you would have the deep clone here, which now defines another copy policy called list of deep. And now the values here are flagged as deep, so which means that now we should use their copy policy when we do clone this structure. And this means that we have to now call the clone methods down here. And then we'll recursively use, again, the copy signature for the next elements to define what should be done with the rest of the list. So that's basically the annotation language, and it's not more complicated than that. It can be summarized pretty shortly as saying that, so a policy is something that has the name copy, gives a name, and then you just annotate fields in that particular class that you want to specify how to copy. And the annotation can either be shallow, which means basically just we're not going to trace this any further, and it can be deep, and then it can have a name and policy associated with it. The idea is, so intuitively what this policy specifies is that, well, you have a heap cell, because what we're talking about, heap cells in memory, that will be reachable from the result of such a call to a method that respects this policy. If you only follow these deep methods, then you should have something fresh, and you should not be reachable from any local variable in the other structure from elsewhere. So that's the summary of the language of annotations. Now, if we want to move to the enforcement part of it, then enforcing non-sharing of dynamically allocated structures is not something that's that straightforward, because you have to keep track of these rather involved structures. What comes to rescue here is that copy methods are generally simple, and we did fix ourselves that we want to we limit ourselves to verify what's called reasonable, in quotes, copy methods. In certain cases, they're just straight line code, actually. So this means that, well, to do the enforcement, we've adopted something that's known as being a fairly heavy-handed static analysis called shape analysis, but made a low adaptation of this and taken out a bit of the strength of the shape analysis, make a more local version of it. So what we do is that the shape analysis that we'll do is that we abstract the memory here by what we call a shape graph. And the shape graph's got several elements. So in the shape graph, you might just have first the local variables of your method that will point to nodes in this graph. So this says that from local variable x, you can access memory that respects this structure described by the rest of the graph. And then you have nodes, and we have two kinds of nodes. We have nodes that say this node represents a memory cell, and it actually represents only just one memory cell. Because other nodes might have to summarize and talk about a whole part of the memory and just represent everything what's going on in a section of the memory. So we have those two kinds of nodes, and of course when you know that something is just one cell, you'll see